300 feet underground, beneath farms and highways on the border of France and Switzerland. The largest machine ever built just broke the laws of physics. Particles are decaying in ways that should be impossible. A magnetic ghost hid inside one accelerator for over 20 years. And two separate experiments, running billions of collisions, are both pointing at something that our best math cannot explain. A hidden force, a new particle, something we have never seen. If you enjoy this, like and subscribe. It helps more than you know. We are going underground. We begin now. Picture a circle, a perfect, massive circle buried 300 feet underground. It stretches so wide that if you stood at one end and looked across, the far side would vanish over the horizon. That circle is 16 miles around, the same distance as driving from downtown Manhattan to JFK Airport. And inside it, one of the strangest things humans have ever built is quietly running. This is the Large Hadron Collider. It sits beneath the border of France and Switzerland, threading under farms, highways, and small towns without anyone above ground feeling a thing. The tunnel itself is wide enough for a person to crawl through. The machine inside it accelerates tiny particles called protons, which are far smaller than a grain of sand, to nearly the speed of light. Then it smashes them together, on purpose, billions of times a day. Why would anyone do that? Because when two protons collide at that speed, they briefly recreate conditions from just after the Big Bang. For a fraction of a second, the collision produces a tiny fireball of raw energy, and inside that fireball, rare particles appear. Particles that normally do not exist in our world. Physicists photograph those particles the moment they appear, studying them before they vanish. The machine was built because science had a problem, a big one. For decades, physicists had a rulebook, a detailed mathematical description of every known particle and every known force in the universe. They called it the Standard Model. It predicted the results of experiments with stunning accuracy. For a long time, every test confirmed it. Every single one. But the Standard Model had gaps. It could not explain gravity at the quantum level. It could not account for dark matter, the invisible substance that makes up most of the mass in the universe. It offered no reason why matter survived after the Big Bang instead of cancelling out with antimatter. The rulebook worked, but it felt incomplete, like a map that shows every road in a city but leaves an entire neighborhood blank. So scientists built the largest instrument in human history to push the rulebook to its breaking point. The pipes inside the collider are kept colder than outer space. The vacuum inside is emptier than the void between galaxies. Every technical detail was designed to create the most controlled, extreme conditions possible so that the results would be clean and trustworthy. Years of engineering, billions of dollars, thousands of physicists from over 100 countries working together, and for a while, the machine confirmed the rulebook again and again. The particles appeared, the data matched, the Standard Model held. Then something changed. The first hint did not come from a dramatic explosion of data. It came from something disappearing. Deep inside one of the accelerators that feeds particles into the main collider, beams of particles began vanishing, quietly, consistently, with no explanation anyone could find. Scientists noticed it. Then they argued about it. Then they spent 20 years trying to locate it. The machine was losing particles to something invisible, something that bent their paths and threw them off course without leaving a trace in any of the normal measurements. They had a ghost, and catching that ghost would eventually lead them to something far more unsettling than a missing particle beam. Most people hear particle collider and picture a giant explosion, something dramatic, a Hollywood moment. The reality is stranger and somehow more impressive. A proton is unimaginably small. If you scaled an atom up to the size of a football stadium, the proton at its center would be about the size of a marble. Now imagine firing two marbles at each other from opposite ends of that stadium at a speed just barely slower than light. They hit. And in the instant of that collision, the energy compresses so intensely that the fabric of matter itself briefly unravels. New particles pop into existence from pure energy. They last for only a tiny fraction of a second before decaying into even smaller particles. Sensors surrounding the collision point record every trail, every signal, every flash of energy. The data floods in faster than any human could process. So, algorithms sort it in real time, flagging the collisions that look unusual and erasing the rest. This process is how physics works at the deepest level. You cannot look directly at a proton. You cannot hold it up to a light. You smash it and study what flies out. It is a little like trying to understand a pocket watch by throwing two of them together at high speed and examining all the tiny pieces that scatter across the floor. The particles that appear in these collisions follow rules. Strict mathematical rules. A particle can only decay into certain combinations of other particles. It can only appear under certain conditions. The entire framework of the Standard Model is built on these rules. Physicists wrote the equations. The machines tested them. For decades, the results matched. But here's the thing about rules. They only stay rules until something breaks them. Each collision lasts less than a trillionth of a second. But the sensors around the collision point are so sensitive that they can track individual particles across a space smaller than a human hair. The sheer volume of data is staggering. Algorithms instantly erase the vast majority of what the sensors record because there is simply too much to store. Only the unusual events get saved. Only the unexpected ones. That design choice means the machine is always hunting for anomalies. Every time the data does not match the prediction, a flag goes up. Most of the time, those flags turn out to be nothing. Random noise, statistical accidents. Scientists have learned to be skeptical, but some flags kept coming back. The same patterns, over and over, in data collected across years. The Standard Model predicted one outcome. The machine kept showing something slightly different. At first, the difference was small enough to argue about. A rounding error, a measurement glitch, something in the hardware. Except the hardware was fine, and the rounding was right. And the glitch, it turned out, was in the rulebook. The collider was not malfunctioning. It was doing exactly what it was designed to do. It was finding the places where our understanding of the universe was wrong. And one of the first places that wrongness showed up was in a particle so small and short-lived that most people had never heard of it, a particle called a B-meson. It existed for less than a trillionth of a second. Then it decayed. And the way it decayed was sending alarm signals through physics labs across the planet. But before we get to that, something even older and stranger demanded attention first. In the 1960s and 70s, physics was having its best decade. Theorists were building equations that described every known particle and every known force with the kind of precision that felt almost magical. A particle would be predicted on paper, and within years, sometimes months, experiments would find it exactly where the math said it would be. By the time the dust settled, the framework had a name, the Standard Model, and it was, by any measure, the most successful scientific theory ever written. It describes everything made of matter, every atom in your body, every photon of light hitting your eyes, every force that holds nuclei together, and every process that makes stars burn. The Standard Model captures all of it in a set of equations that fit on a single page. Physicists call it elegant. Some call it beautiful. A complete description of reality compressed into pure math. The particles it describes fall into two families. There are the building blocks, called fermions, which include quarks and leptons. Quarks combine to form protons and neutrons, which build atomic nuclei. Leptons include the electron, which orbits those nuclei, and three other related particles. The second family covers the force carriers, called bosons, which transmit the fundamental forces between particles. Light itself is a boson, the particle that gives everything mass. the Higgs boson, is a boson. Physicists spent decades hunting it before finally confirming its existence in 2012. The Standard Model also describes 3 of the 4 known fundamental forces: electromagnetism, which governs light and electricity; the strong nuclear force, which holds protons and neutrons together inside atomic nuclei; and the weak nuclear force, which controls radioactive decay. The model explains how these forces work, how strong they are, and how they interact with matter. For a long time, every experiment confirmed it. Every single test across hundreds of experiments in dozens of countries produced results that matched the predictions. The Standard Model felt airtight, but it had 3 problems it could never fix. Gravity refused to fit. The Standard Model has no quantum description of gravity. It cannot explain what happens to gravity at the smallest scales of reality. Physicists have tried for decades to squeeze gravity into the framework. Every attempt fails. Dark matter refused to appear. Astronomers know that most of the mass in the universe is invisible. Galaxies rotate in ways that only make sense if enormous amounts of unseen matter are pulling on them. The Standard Model describes none of the particles that could account for that mass. They simply are not in the equations. And the matter-antimatter mystery refused to solve itself. When the Big Bang happened, it should have created equal amounts of matter and antimatter, which would have destroyed each other completely, leaving nothing behind. Something tilted the balance toward matter. The Standard Model cannot explain what. So physicists knew the rulebook was incomplete. They just did not know where the gaps were hiding. The Standard Model kept passing every test thrown at it, even as the universe kept hinting that something deeper was out there. The Large Hadron Collider was designed to find those gaps. And years into its operation, something finally cracked. The first crack was quiet, easy to dismiss. A beam of particles, slowly losing members, with no one able to explain where they were going. A scientific theory does not break all at once. It splinters. One experiment produces a result that is slightly off. Another team checks the math and finds no error. A third experiment runs the same test and gets the same strange result. The cracks start small and multiply slowly, until one day there are too many to explain away. That is the story playing out at CERN right now. The first wave of suspicion did not involve a dramatic new discovery. It involved something much quieter. Scientists began noticing that certain particles were not behaving the way the Standard Model predicted when they decayed. Decay, in physics, means a particle transforming into smaller, lighter particles. Every known particle has a specific set of ways it can decay, specific products, specific ratios. The Standard Model maps all of them out precisely. When a particle decays, it is supposed to follow those rules exactly, like a recipe. The same ingredients go in, and the same dish comes out every time. If the dish ever changes, something has gone wrong with the recipe, and the dish was changing. The first hints were subtle enough to dismiss. Single experiments produce flukes all the time. Random statistical noise can make a result look meaningful when it is not. So scientists at CERN did what scientists always do. They collected more data, they ran more collisions, they checked the equipment, they tested alternative explanations, they waited for the pattern to disappear. It did not disappear. Across multiple experiments, across years of data collection, certain particles kept decaying in slightly wrong ways. The ratios were off. The products were appearing at the wrong frequencies, and the deviations, though small individually, were pointing in the same direction every single time. That consistency is what scared physicists. A random error scatters in all directions. A systematic one points somewhere specific. The data was pointing at something the Standard Model had never predicted and could not account for. But there was something else happening at the same time. Something separate and equally unsettling. Inside one of CERN's other accelerators, the machine that feeds particles into the Large Hadron Collider, particles were not just decaying strangely, they were vanishing entirely. disappearing from the beam mid-flight. No record, no signal, just gone. A beam of particles at CERN is not a casual thing. It is a precisely engineered stream of subatomic matter, guided by powerful magnets, measured continuously, designed to arrive at its destination with exact precision. Losing particles from a beam should be impossible to miss. And yet, for years, the losses kept happening, and no one could find the cause. Engineers checked the magnets, physicists reviewed the alignment, teams looked at the power systems, the vacuum seals, the sensors. Everything appeared normal, everything tested clean, and still, the particles disappeared. The losses were not dramatic enough to shut the machine down. They were just persistent, annoying. A small percentage of the beam going missing on every pass through the accelerator. The kind of problem that sits in the background of a research facility for years, while more urgent work takes priority. It sat in the background for over 20 years. And the thing that was stealing those particles turned out to be something no one had thought to look for. Something that required an entirely new kind of map to even see. It earned a nickname, the Ghost. Physicists at CERN's superproton synchrotron, the massive accelerator that feeds particles into the main collider, had been watching particles vanish from their beams since the 1970s. Every few passes through the machine, a small fraction of the beam would go missing. The losses were consistent, repeatable, and completely invisible to every instrument they had. The superproton synchrotron is enormous. It measures about 4 miles around. Inside it, particles travel in a loop, guided by hundreds of powerful electromagnets arranged in a careful sequence. The magnets steer the beam and keep it tight and focused. When everything works correctly, the beam circulates with almost no loss. But this machine was losing particles, quietly and steadily, and no instrument in the facility could see what was causing it. The Ghost did not trip any alarms. It left no obvious trail. The magnets looked fine on every readout. The beam alignment appeared correct. Diagnostic systems showed nothing unusual. From every standard measurement, the machine was functioning normally. And yet the particles kept disappearing. Scientists suspected a magnetic resonance. In physics, resonance happens when a system gets nudged at just the right rhythm to build up energy. Think of pushing a child on a swing. A small push at exactly the right moment adds up over time into a much bigger swing. Inside the accelerator, tiny rhythmic pushes from magnetic fields could build up and knock particles sideways, throwing them out of the beam. The particles would not slow down dramatically. They would just drift off course until the walls of the pipe caught them. The problem was proving it. A magnetic resonance inside a circular accelerator is invisible to normal geometry. The beam travels in a loop. The resonance shifts over time. The structure of the disturbance, if it existed, was three-dimensional and changing. You cannot draw it on a flat map. You cannot find it with standard instruments pointing in standard directions. For over 2 decades, the Ghost haunted the machine. Scientists filed reports about the mysterious losses. Teams proposed explanations, tested them, and found nothing. The problem became a piece of background noise at the facility. Everyone knew it was there. Nobody could catch it. And the longer it went unsolved, the more uncomfortable it became. Because the superproton synchrotron was supposed to be one of the most controlled, well-understood accelerators in the world. If something invisible could hide inside it for 20 years without being detected, it raised a disturbing question. What else was hiding in machines physicists thought they fully understood? That question did not stay theoretical for long. In 2024, a team decided to stop looking for the Ghost using traditional methods. They designed something new. They placed highly sensitive particle monitors at dozens of points along the accelerator and tracked beam behavior across thousands of individual passes. They were going to find the Ghost by watching every move it made, one beam at a time, over days and weeks of continuous measurement. What they found was stranger than anyone expected. The Ghost was real, and mapping it required math that operates in 4 dimensions. Scientists are comfortable with 3 dimensions: length, width, height. Everything in our physical world fits inside those three. We build our instruments to measure in 3 dimensions. We draw our maps in 3 dimensions. We design our accelerators using 3-dimensional geometry. That was the problem. The magnetic disturbance hiding inside the superproton synchrotron was a 3-dimensional structure that changed over time. The time element made it 4-dimensional, and 4-dimensional structures cannot be captured by instruments designed for 3. Every measurement they took was like trying to photograph a moving object with a camera that only captures still images. The picture was always incomplete. To understand why this matters, think about a shadow. If you shine a light on a 3-dimensional object, the shadow on the wall is 2-dimensional. It shows you some information about the object, but it loses depth. If the object is spinning, the shadow changes shape. You could watch the shadow for hours and never fully reconstruct what the object actually looks like, because a crucial dimension is missing from your view. That is exactly what was happening inside the accelerator. Every diagnostic tool the engineers used was essentially taking a 2-dimensional shadow of a 4-dimensional problem. The readouts looked normal because the instruments were only capturing a slice of what was actually happening. The magnetic resonance inside the machine was not a single, fixed field sitting in one place. It was a coupled resonance, meaning 2 different types of magnetic motion were linked together and influencing each other at the same time. The beam's horizontal sway and its vertical bounce were connected by this hidden field. As the beam circled through the machine, the resonance shifted slightly with each pass. It was a structure that moved through time while also occupying 3 dimensions of space. Standard instruments checked horizontal, they checked vertical, they checked the obvious frequency ranges. But because the resonance was coupled, checking each axis independently gave a false, clean reading. The real signal only appeared when you looked at the relationship between the axes across thousands of passes. A pattern hidden inside the patterns. This is why the ghost survived undetected for so long. It was not hiding from careless scientists. It was hiding from the geometry of their tools. Once physicists understood this, they realized something uncomfortable. If this kind of hidden, time-evolving magnetic structure could exist inside the most studied particle accelerator on Earth without detection for over 20 years, then any accelerator anywhere in the world might contain similar invisible disturbances. The machines that generate the data physicists trust to test the laws of physics might themselves be introducing errors that look like clean measurements. Every result from every accelerator experiment suddenly needed a new layer of scrutiny, and that scrutiny was about to get much more intense. Because while the ghost problem was a mechanical mystery, a puzzle about magnetic fields and accelerator design, the anomalies appearing in collision data were something else entirely. They were a sign that the particles themselves were misbehaving, following rules that the standard model did not write. The hunt for the ghost was over. The hunt for something far harder to explain was just beginning. For 2 decades, nobody could find it with the old tools. So in 2024, a team at CERN decided to build new ones. The plan was precise and slow. Instead of measuring the beam at a few points with standard equipment, they placed highly sensitive monitors at dozens of locations along the superproton synchrotron's 4-mile loop. These were not standard diagnostic sensors. They were instruments capable of tracking the exact position and angle of individual particle bunches with extreme precision, capturing tiny movements that previous tools would have averaged out and ignored. Then they ran the beam. Over and over. 3,000 separate beam passages, each one recorded in full detail. Scientists watched the data accumulate day after day, tracking how the beam shifted from one pass to the next, looking for a pattern that only became visible across thousands of repetitions. It is worth pausing to appreciate what 3,000 beam passages means. Each pass happens in a fraction of a second. The particles are traveling at nearly the speed of light. In the time it takes you to blink, the beam completes several full laps around the 4-mile ring. 3,000 passes represent an enormous volume of information, billions of individual data points, all of which needed to be processed and compared to find a signal buried in the noise. The signal appeared. It was not dramatic. It showed up as a tiny, rhythmic wobble in the beam's position that grew stronger in a specific pattern across multiple passes. The wobble had a structure. It was not random. It repeated with a specific phase, meaning the disturbance was synchronized to something happening inside the magnetic system of the accelerator. When the team mapped the wobble mathematically, the shape of the disturbance emerged. It was a coupled resonance, two axes of motion linked together by a hidden interaction inside the magnets. The beam was swaying side to side and bouncing up and down, and those two motions were connected by an invisible magnetic force that tied them together. As the beam circled the ring, the resonance rotated and shifted slightly each time. The structure was three-dimensional, and it evolved with each pass through the machine, which made it four-dimensional. 4 dimensions of behavior, hiding in a machine that engineers had been measuring in 3 dimensions for 50 years. Mapping the full structure required new mathematical tools. The team used what physicists call normal form analysis, a method designed to untangle coupled systems by transforming coordinates so that the hidden relationships become visible. Think of it as changing the angle of your camera until the shadow on the wall finally shows you the shape you could not see before. Once they applied those tools, the ghost snapped into focus. The team could see exactly how the magnetic resonance formed, how it shifted across passes, and how it knocked particles out of the beam one by one until enough were gone to show up as a measurable loss. The ghost was real, and it was a natural consequence of tiny, unavoidable imperfections in the accelerator's magnets. But understanding the ghost raised a new question immediately. If magnetic imperfections could hide a 4-dimensional resonance inside the best-studied accelerator on Earth for 50 years, what else might imperfections be hiding in the collision data? That question had no comfortable answer. Most of physics lives in 3 dimensions. That is the world we navigate. That is the geometry our instruments are designed to measure. When the team at CERN discovered that the ghost inside the superproton synchrotron required 4-dimensional mathematics to describe, it was a jolt, a reminder that the universe does not care what our instruments are built for. The phrase 4 dimensions makes people think of science fiction, hidden realms, invisible layers of reality stacked on top of the visible one. The actual meaning is both more ordinary and more strange. 4 dimensions, in this context, means 3 dimensions of space combined with time. A structure that exists not just in length, width, and height, but also changes as time passes. A shape that you cannot fully describe without saying where it is and when. The coupled resonance inside the accelerator was exactly that kind of structure. Its physical shape in space was 3-dimensional, a twisting, rotating pattern of magnetic influence spread around the 4-mile loop. But that pattern shifted slightly with every pass the beam made. The shape you measured on pass 1 was different from the shape on pass 200. To describe the full structure, you had to track how it evolved across thousands of cycles. That is what 4 dimensions means here, a thing that moves through time while also occupying space. The mathematical method used to map it, normal form analysis, works by rewriting the coordinates of the system so that the hidden couplings become visible. In plain terms, think of it like switching from a regular map to a map that shows elevation. The original map was accurate, but flat. Adding elevation reveals a mountain range that was invisible before. Normal form analysis added the extra dimension that the ghost had been hiding behind. Once the structure was mapped, scientists could explain every aspect of the particle losses. The resonance knocked particles slightly off course each time the beam passed through the affected region. The effect accumulated over many passes. Small deviations compounded until individual particles drifted too far from the center of the beam and hit the walls of the pipe. The losses were gradual, consistent, invisible to instruments that measured each pass separately instead of tracking the pattern across thousands. What makes this discovery genuinely unsettling is the scale of the oversight. The superproton synchrotron has been running since the 1970s. It has generated data used in some of the most important particle physics experiments in history. For 50 years, this four-dimensional structure was present in the machine, quietly affecting the beam, and nobody detected it because the tools being used were not designed to see it. Scientists are now asking whether similar structures exist in other accelerators. Every high-energy particle machine relies on powerful magnets with microscopic imperfections. The physics that produces coupled resonances is not unique to one machine. The math that hides these structures from conventional diagnostics applies broadly. That question does not have a comfortable answer yet. And while the accelerator team was grappling with this mechanical mystery, a separate group of physicists was staring at collision data that raised a completely different kind of alarm. The particles produced in those collisions were breaking a rule the standard model considered absolute. The magnets inside a particle accelerator look, from a distance, like engineering perfection. They are enormous, precisely wound coils of superconducting wire kept at temperatures colder than outer space. They generate fields strong enough to bend a beam of particles traveling at nearly the speed of light around a 4-mile curve. The tolerances involved are extraordinary. These machines are built to millimeter precision across miles of tunnel, and yet no magnet is perfect. At the microscopic level, every superconducting magnet has flaws, tiny variations in the density of the wire, minuscule misalignments in the coil geometry, microscopic inconsistencies in the material itself. Each individual flaw is so small that it has essentially no measurable effect on any single pass of a particle beam. The field it produces deviates from ideal by an amount far smaller than any standard instrument can reliably detect. But particles do not make one pass. They make thousands. Inside a circular accelerator, a beam of particles loops around the ring continuously. Each loop brings the same particles back through the same magnets. Each pass through an imperfect magnet applies another tiny nudge to the beam. The nudges accumulate. Over hundreds of passes, what began as an imperceptible deviation grows into a measurable drift. Over thousands of passes, the drift becomes significant enough to push particles out of the beam entirely. This is resonance at the microscopic scale. A force so small it registers as nothing, repeated at just the right rhythm, building into something real. Like tapping the same spot on a bridge railing at exactly the right frequency until the vibration becomes visible. The magnet imperfections in the superproton synchrotron created exactly this effect. The horizontal and vertical motions of the beam were each being nudged by slightly different fields. Over time, those nudges synchronized. The two axes of motion became coupled, meaning a push in one direction produced a corresponding drift in the other. The coupling created a resonance that rotated and evolved with every pass, a four-dimensional structure born from a collection of microscopic manufacturing errors. What this tells us about physics is important. The universe amplifies small things. Given enough time and enough repetition, a nearly invisible force can become a dominant one. That principle operates everywhere, from the way erosion carves canyons to the way gravitational tugs from neighboring moons destabilize orbits. Particle accelerators are not immune to it. The deeper lesson is about measurement. Scientists trust their instruments. They calibrate them carefully. They check their results against theoretical predictions. But if the instruments are designed around assumptions that miss a hidden dimension of a problem, those instruments can give consistently clean readings, while a real effect hides just outside their view. The ghost proved that, and it forced a question onto every physicist paying attention. If this kind of hidden, accumulated effect can live inside a machine for 50 years without detection, what is hiding inside the collision data generated by that machine? The answer to that question was starting to arrive from a completely different part of CERN, from an experiment that had been quietly analyzing hundreds of billions of collisions, looking for patterns in the way one specific particle transformed when it broke apart. That particle was called a B-meson, and its behavior was about to cause a crisis. Solving the ghost should have been a relief. The particle losses explained, the magnetic resonance mapped, the four-dimensional structure understood, a 50-year mystery closed. Instead, it made things worse. The moment physicists understood how a hidden resonance could evade detection inside a well-monitored accelerator for half a century, a wave of doubt spread through the field. Every major particle physics experiment in the world runs on data produced by accelerators. Every result that has confirmed or challenged the standard model over the past decades was built on measurements taken by instruments designed around the same three-dimensional assumptions that missed the ghost. Were there similar hidden structures in other machines? Were other accelerators losing particles to four-dimensional resonances that no instrument had yet been designed to detect? And most uncomfortably, were some of the anomalies physicists had dismissed over the years as instrument error actually real signals buried under measurement distortions? No one had a quick answer to any of those questions. The ghost discovery also reframed something that had already been worrying physicists for years. Data from the Large Hadron Collider's main experiments had been showing strange patterns in particle decays. Specific particles were transforming in ways that slightly but consistently deviated from standard model predictions. The deviations were small enough that some scientists attributed them to measurement uncertainty. The ghost discovery put new pressure on that explanation. If the most carefully monitored accelerator at the world's most advanced physics facility had harbored an invisible, measurement-distorting structure for 50 years, the argument that anomalies in decay data were just measurement noise became harder to make. Maybe the anomalies were real. Maybe the particles genuinely were doing something wrong. Maybe the standard model was failing. The question was no longer theoretical. It was urgent. And the urgency came with a name: the B meson, a short-lived particle produced in enormous quantities during high-energy collisions. Scientists at CERN had been analyzing B meson decays for years, slowly building up a dataset large enough to say something definitive. By the time the ghost was solved, that dataset had grown to 650 billion recorded collisions. 650 billion. The results from that data were pointing somewhere the standard model had never predicted, somewhere that, if confirmed, would require the entire framework to be rebuilt from the ground up. But before understanding what the B meson was doing, it helps to understand what the standard model had promised about how all particles behave. There was a rule so fundamental that physicists had built enormous machines to test it, a rule called lepton universality. It said that the forces of nature treat all matter particles equally, with no exceptions. That rule was about to be challenged in a way that even the most skeptical physicist could not dismiss. Some particles live for millions of years, others survive for millionths of a second. And then there are particles like the B meson, which exists for such a brief moment that calling it short-lived feels like a massive understatement. A B meson survives for about 1/1,000,000,000th of a second after it forms. In that time, it travels only a few millimeters, less than the width of your pinky nail, before breaking apart into smaller particles. It exists, it decays, and it is gone. The entire life cycle happens faster than any human process, faster than any chemical reaction, faster than the signal in a computer chip. So why do physicists care so much about something that tiny and that brief? Because the way it breaks apart is a fingerprint. Every particle decays according to fixed rules. Those rules come directly from the standard model. The B meson can decay through multiple different channels, meaning it can transform into different combinations of lighter particles depending on which quantum pathway it takes. Physicists know exactly which channels are possible and exactly how often each one should occur. The ratios are precisely calculated. When B mesons form in a collision and then decay, the sensors surrounding the collision point track the daughter particles that fly outward. By collecting millions of those decay events and comparing the frequencies of different decay channels, physicists build a statistical picture of how the B meson behaves. The B meson contains something called a beauty quark, which is one of the 6 types of quarks that make up the particle families of the standard model. Beauty quarks are heavier than most, which means B mesons carry more energy and have more possible decay channels than lighter particles. That variety makes them extremely useful for testing the standard model. More channels means more opportunities for something unexpected to appear. The experiment designed to study B mesons at CERN is called the Large Hadron Collider Beauty Experiment. Its entire purpose is to capture and analyze B meson decays in enormous volumes. Over 7 years, from 2011 to 2018, it recorded and stored the results of 650 billion particle collisions. The scientists then spent years analyzing those results, looking for any deviation from what the standard model predicted. They found one, and it kept growing larger the more data they added. The deviation appeared in a specific type of decay called an electroweak penguin decay. This oddly named process involves the beauty quark inside the B meson transforming through a rare quantum pathway. The standard model predicts that when this happens, the B meson should produce two types of lighter matter particles called leptons. At a specific equal ratio, electrons and their heavier cousins, called muons, should appear at the same rate. They were not appearing at the same rate. The muons were showing up less often than the standard model predicted. The difference was small, but it was consistent across years of data. And consistency in physics is everything. Something was interfering with the muons, something the standard model had no equation for, something invisible to every instrument at CERN, something that was bending the rules of a framework physicists had spent 60 years building, and the B meson was carrying the proof. Every framework needs a foundation, a set of assumptions so basic that everything else is built on top of them. In the standard model, one of those foundations is a principle called lepton universality. The idea is elegant. The fundamental forces of nature, the weak force, electromagnetism, and the strong force do not have favorites. They treat all matter particles in the same family equally. A muon, which is essentially a heavier version of an electron, should interact with the weak force in exactly the same way an electron does, scaled by mass, with no extra preferences, no secret weighting, no hidden thumb on the scale. Lepton universality means the laws of physics are fair. Every particle of the same type gets the same treatment from the same force. The mathematical predictions of the standard model are built on this assumption. Every calculation involving particle decays, every ratio of expected outcomes, every predicted frequency assumes that lepton universality holds absolutely. If it breaks, the math breaks with it. The idea was tested many times over the decades and always confirmed. Experiments at different facilities around the world produced results consistent with equal treatment of leptons. Physicists became confident in it. It felt secure, certain, but confidence built on limited data is a trap. The Large Hadron Collider Beauty Experiment was designed with the specific capability to test lepton universality at a level of precision no earlier experiment could reach. By recording hundreds of billions of B meson decays and comparing the rates at which those decays produced electrons versus muons, scientists could check the equality assumption with extraordinary statistical power. What they found was a gap. Muons, the heavier cousins of electrons, were appearing in certain B meson decay channels less often than the standard model's equal treatment prediction required. The deficit was small, around 10% below predicted levels. On any single experimental run, a 10% deviation could be noise, random fluctuation, a bad measurement. Scientists have learned not to trust small gaps from individual experiments. But this gap appeared in every subset of the data: early runs, late runs, different calibration periods, different detector configurations. Every slice of the 650 billion collision dataset showed the same pattern: muons slightly underrepresented, consistently. Across years and billions of events, that kind of consistency is the signature of a real effect. Random errors average out. Systematic ones persist. The most straightforward interpretation was uncomfortable. The weak force was treating muons differently from electrons. The principle of equal treatment, lepton universality, the bedrock assumption that physicists had trusted for decades, was behaving as though it had an exception, a hidden bias built into nature itself. If that interpretation held up, It would mean every calculation in the standard model that assumes lepton universality carries a flaw. Every prediction that depended on equal treatment would need to be re-examined. The framework was intact on the surface. Beneath the surface, something was pulling in a different direction. Physicists needed to know what, and they needed one more thing before that question could be answered. They needed a number large enough to rule out luck entirely. That number was coming, and when it arrived, it would land like a signal flare over the whole field of physics. Numbers in physics get large fast. Atoms are small, forces are tiny, energies are enormous. Scientists spend their careers working with values so extreme they stop feeling real. But 650 billion collisions is a number worth pausing on. 650 billion individual moments of two protons traveling at nearly the speed of light and meeting head-on inside a tube thinner than a water pipe, each one generating a tiny fireball of energy lasting less than a trillionth of a second, each one producing a spray of particles that shoot outward through layers of sensors, leaving signals that algorithms read and sort in real time, each one either flagged as interesting or erased instantly to make room for the next. The Large Hadron Collider beauty experiment recorded the interesting ones. Over 7 years, from 2011 to 2018, the experiment captured the data from every B-meson decay event its sensors could identify. The result was a dataset so large it took years to fully analyze. To put the scale another way, 650 billion is roughly 80 times the number of people who have ever lived on Earth. If each collision were a single grain of sand, the pile would fill a large room from floor to ceiling. Size matters in statistics. The larger the dataset, the smaller the noise. Random fluctuations, the kind that make a small experiment look like it found something real when it found nothing, wash out as the numbers grow. A result that looks significant with 1,000 events might vanish at 10,000. But a result that holds at 650 billion events is a different situation entirely. The B-meson decay anomaly held. Scientists spent years checking it. They divided the data into subgroups and tested each one separately. They looked for hardware problems that might affect muon detection differently from electron detection. They ran the analysis with different software versions. They brought in outside teams to verify the methodology. They looked for every possible way the result could be wrong. It was not wrong. The pattern survived every check, muons appearing less often than predicted, consistently across every subset, every reanalysis, every calibration correction. The data was clean and the signal was real. The collaboration published results showing a deviation from standard model predictions that kept improving in statistical significance over time. By 2026, the anomaly had reached a level physicists call 4 sigma. That number needs context. In particle physics, a result is considered significant when it crosses 3 sigma. That means there is roughly a 1 in 700 chance. The result is a random statistical accident. 4 sigma raises the bar to 1 in 16,000. The odds that the B-meson anomaly is nothing but noise are 1 in 16,000. For context, that is roughly the same as flipping a coin and getting heads 14 times in a row, and then doing it again the next day, and getting the same result. Physicists stop dismissing things at 4 sigma. They start taking them seriously as signals of real physics. And this signal was pointing directly at something outside the standard model, something interacting with the decay process in a way the rulebook had never accounted for. The B-meson was carrying the evidence, but it was carrying it alone. That was about to change. The B-meson breaks apart. That much is certain. What comes out when it does is where the story gets strange. When a B-meson takes the specific decay path scientists were watching, the one involving the beauty quark transforming through a rare quantum process, it should produce a pair of leptons, one electron or one muon, paired with its antimatter partner. The standard model says both possibilities happen at equal rates. Adjusted for the mass difference between muons and electrons, the math predicts a ratio extremely close to 1 to 1. The measured ratio was off. Muon pairs appeared at a rate about 10% lower than predicted. Electron pairs appeared roughly as expected. The imbalance was not between two random channels, it was precisely between the two lepton types. That specificity is what made it disturbing. A blanket measurement error would affect both channels similarly. A calibration problem with the detector would not know the difference between an electron and a muon. But this deviation showed up in muon production only. Whatever was causing the deficit was specifically affecting muons, not electrons. Something in the decay process was treating the two lepton types differently. In physics, when something breaks a symmetry, it means a force is involved. Symmetry in this context means equal treatment. If the forces governing B-meson decay treated muons and electrons the same way, lepton universality held and the ratio stayed at 1:1. When the ratio deviated, it meant something was applying unequal force. Something was tipping the scale against muon production in this specific decay channel. The standard model contains no particle or force that could do this. Every known interaction inside a decaying B-meson had been accounted for. The calculations were complete. There was no room in the existing equations for a new thumb on the scale, which meant the thumb was coming from outside the equation. Physicists began talking about new physics. The phrase means any phenomenon that exists outside the known framework, a new particle, a new force, a hidden interaction that the standard model never predicted because nobody had yet built a machine sensitive enough to detect it. The data from 650 billion collisions was not describing a mistake in the experiment. It was describing a gap in the theory, and the gap was shaped like something real. The muon deficit had a specific magnitude, a specific dependence on energy, a specific pattern of occurrence across different decay channels. That pattern constrained what the new physics could be. Whatever was causing the deficit had to interact with muons more strongly than with electrons, had to appear in weak force decays, and had to carry specific properties to match the measured numbers. Theorists started writing papers, proposing candidates for the unknown force or particle, calculating whether their models matched the data. The conversation in physics shifted from whether the anomaly was real to what was causing it. But even as that conversation was gaining momentum, another anomaly was surfacing from a different experiment at a different accelerator, a different particle, a different decay channel, a different team, the same direction of trouble. That second signal came from something much smaller and rarer than a B-meson, and the confidence level it reached would clear even the highest bar in experimental physics. 4. Sigma. Two words that carry enormous weight inside a physics lab. To understand why, you need to understand what physicists mean by sigma. It is a unit of statistical confidence. Specifically, it measures how unlikely a result is to be a random accident. 1 sigma means there is roughly a 1 in 3 chance the result is noise. 2 sigma drops to 1 in 22. 3 sigma is 1 in 700. 4 sigma is 1 in 16,000. These numbers come from a simple idea. If you flip a fair coin 100 times, you expect roughly 50 heads. If you get 58 heads, that is a little unusual. If you get 70 heads, that is very unusual. Sigma measures how far a result sits from the expected average and converts that distance into a probability. In particle physics, 3 sigma is the threshold for announcing something interesting. 4 sigma is where physicists start genuinely believing a result. 5 sigma, 1 in 3.5 million odds, is the standard for claiming a discovery. The Higgs boson was announced at 5 sigma. The B-meson anomaly reached 4 sigma. That means if the standard model is correct and lepton universality holds perfectly, the probability that the data produced this exact deviation purely by chance is 1 in 16,000. Those are not good odds for randomness. Reaching 4 sigma across 650 billion collisions, across 7 years of data, across multiple independent verification checks, represents a level of certainty that forces physicists to take a result seriously. It moves the conversation from, could this be real, to, if this is wrong, where exactly is the error? and the teams working on this anomaly had already spent years looking for the error. They found none. The statistical power of the dataset made the result robust against almost every objection. Machine learning algorithms had cross-checked the decay classifications. Multiple independent analysis teams had worked through the same data using different methods. The collaboration had published results that other groups had scrutinized for flaws. The 4 sigma level survived all of it. For a single anomaly, 4 sigma is compelling. For an anomaly that aligns with theoretical predictions of specific new particles, it is harder to dismiss. And for an anomaly that appears at the same time as a separate, independent anomaly pointing in the same direction, it becomes a pattern. Patterns in physics are not coincidences. They are evidence. The B-meson result was standing at 4 sigma with no explanation inside the standard model. And simultaneously, a separate experiment had been watching a completely different particle, a particle called a kaon, a particle that decays through a pathway so rare that finding it at all should have taken years of dedicated work. Scientists found it, and then they found that it happened far more often than the standard model allowed. The kaon result did not land at 4 sigma, it landed at 5. The name sounds like a joke. Physicists have a reputation for dry humor, and the electroweak penguin decay is a prime example. It was named in 1977 during a late-night discussion where one physicist bet another that he could work the word penguin into a scientific paper. He won the bet. The name stuck, and now one of the most important decay processes in modern particle physics carries the image of a bird that cannot fly. But the physics behind it is anything but funny. The electroweak penguin decay is a specific quantum process that happens inside a B-meson when the beauty quark changes into a strange quark. The word electroweak refers to the combination of 2 fundamental forces, electromagnetism and the weak nuclear force, which unify at high energies into a single framework. The decay pathway involves a loop of virtual particles, particles that borrow energy from the quantum vacuum and exist for such a brief moment that they cannot be directly detected, only inferred through their effects. Inside this loop, the beauty quark emits and reabsorbs a force-carrying particle called a W boson while interacting with other quarks. The process also involves a photon or a Z boson. The end result is a B-meson that transforms into particles, including a lepton pair. The specific combination of forces and virtual particles involved makes this decay extremely sensitive to new physics. Any unknown particle with the right properties that slips into the quantum loop would change the outcome in a measurable way. Think of the virtual particle loop as a crowded hallway. Normally, only the particles the standard model predicts can walk through it. If a new particle exists with the right properties, it joins the crowd inside the loop and subtly changes the traffic pattern on the way out. The change is small, but across hundreds of billions of events, it adds up. This is exactly what made the electroweak penguin channel so valuable as a testing ground. The loop process amplifies the effect of anything unexpected. A tiny influence from a new particle gets magnified by the quantum arithmetic of the loop, making it measurable at the macroscopic scale of detector statistics. The Large Hadron Collider beauty experiment was specifically optimized to collect electroweak penguin decays. The geometry of the detector, the trigger algorithms that decided which events to save, the analysis pipelines, all were tuned around capturing these rare events. Scientists knew the channel was sensitive. They built around that sensitivity, and when the data came in across 7 years, the lepton pairs that came out of the electroweak penguin pathway were not balanced. Muons appeared less often than electrons. The imbalance persisted across every analysis. The electroweak penguin loop was behaving as though something extra had slipped into the hallway and was blocking muon production specifically. The standard model had no particle that could do this. Theorists proposed candidates. Some pointed to a particle called a leptoquark, which couples directly to quarks and leptons simultaneously, and would naturally show up inside the penguin loop. Others pointed to a heavy boson carrying a new force that preferentially interacted with muons. Both ideas were theoretical. Neither had been seen. But the evidence that one of them existed was growing stronger with every new analysis. And evidence from the kaon experiment was about to push the crisis to a level that demanded answers. Before there were B mesons, there were kaons. These particles were discovered decades earlier, in the 1940s and 50s, when physicists first started using particle accelerators and cosmic ray detectors to smash atoms and study the debris. Kaons were among the first truly strange particles ever found. In fact, they are the reason the word strange became an official physics term. A kaon is a meson, like a B meson, meaning it is built from one quark and one antiquark. But where a B meson contains a heavy beauty quark, a kaon contains a strange quark. Strange quarks are lighter. Kaons are lighter. They live longer than B mesons, though still for only a tiny fraction of a second, and they decay through pathways that, in some cases, are extraordinarily rare. One pathway in particular became the focus of an experiment at CERN called Na62. This pathway is called the golden channel decay, and it happens when a charged kaon transforms into a charged pion, plus a neutrino and an antimatter neutrino. The standard model allows this decay. It predicts exactly how often it should happen, and the prediction is striking. Fewer than 1 in 10 billion kaons take this path. 1 in 10 billion. If you filled a large stadium with kaons and let them all decay, you would expect fewer than one of them to decay through the golden channel. The other 9,999,999,999 would decay some other way. Finding even a handful of these decays requires producing enormous numbers of kaons and watching them with extreme patience. The Na62 experiment at CERN's superproton synchrotron was built specifically for this purpose. Scientists blasted a high-intensity beam of protons into a fixed target, creating a spray of secondary particles that included vast numbers of kaons. Then they tracked those kaons downstream, waiting for the golden channel signature to appear. The signature itself is almost paradoxical. A kaon goes in, a charged pion comes out, along with 2 neutrinos. But neutrinos do not interact with anything. They pass straight through matter and detectors without leaving a signal. So the experiment could never directly see the neutrinos. Instead, it had to infer their presence by accounting for all the momentum and energy in the system and finding the missing portion. A pion flying out with less total momentum than the kaon carried in meant the missing momentum had gone into neutrinos. Building a detector capable of tracking this invisible remainder across trillions of kaon decays required extraordinary engineering. The measurement uncertainty had to be small enough to distinguish 1 in 10 billion signal events from all the background noise produced by other decays happening at the same time. The experiment ran for years. The data accumulated slowly, one golden channel event at a time. And when they counted the events, the number was wrong. The standard model said a specific quantity would appear at a specific rate. The measured rate was higher, by enough to matter, by enough to mean something, by enough to change everything. Some experiments are built to find the obvious. Others are built to find the nearly impossible. The Na62 experiment belongs to the second category, and everything about its design reflects that ambition. Na62 sits at the end of a long beamline connected to the superproton synchrotron, the same accelerator where the ghost resonance hid for 50 years. The experiment stretches across hundreds of feet of tunnel. Inside that tunnel, an intense beam of particles exits the accelerator, travels through a series of magnets and detectors, and eventually reaches a decay region where kaons are given the chance to break apart. The beam itself is not made of pure kaons. When the proton beam hits the target, it produces a mixed spray of particles, kaons mixed together with pions and other mesons. The first job of the experiment is to identify which particles in the spray are kaons. This requires a specialized detector called a CEDAR, which measures how particles emit light as they travel through a gas at high speed. Different particles emit light at different angles. The CEDAR reads those angles and flags the kaons. Once a kaon is identified, the experiment tracks it continuously as it flies down the decay region. Dozens of tracking detectors line the tunnel, recording the kaon's position and momentum at each step. If the kaon decays, the detectors immediately search for the signature of the golden channel, a single charged pion emerging from the decay point, with a momentum that accounts for only part of the original kaon's energy. The rest, carried invisibly by the two neutrinos, shows up as a gap in the energy budget. Filling that gap with neutrinos is an inference. And inferences in physics require eliminating every other explanation first. That elimination process is brutal. The NA62 team identified over a dozen different decay channels that could mimic the golden channel signature under certain conditions. Each one had to be modeled, measured, and subtracted from the data before the remaining events could be trusted as genuine golden channel decays. Some of the backgrounds were themselves rare decays, occurring in only a few per million kaons. Accounting for them required detailed simulations and careful cross-checks against data collected during dedicated calibration runs. The detector at the downstream end of the experiment plays a critical role. It is a large array designed to veto any particle that reaches it. If a photon or charged particle flies through the decay region and hits the downstream detector, the event is rejected. A genuine golden channel decay should produce nothing downstream except the pion. Everything else gets vetoed. This veto system suppresses the backgrounds by orders of magnitude, isolating the signal events from the noise. Running this experiment for years produces a slow accumulation of golden channel candidates. Each candidate is reviewed against the full battery of selection criteria. Events that pass every check are counted. The NA62 team collected enough confirmed golden channel events to make a statistically meaningful measurement. They compared their count to the standard model prediction. The count was higher than the prediction. The excess was not small enough to attribute to calibration uncertainty, and the significance level of that excess was climbing toward a number that particle physicists treat as a discovery threshold. The kaon was talking, and what it said contradicted the rulebook in a way that could not be explained away. The NA62 team ran their analysis. They checked it. They checked it again. They brought in outside reviewers. They tested the backgrounds, the veto efficiency, the kaon identification rate, and the momentum resolution. They looked for any systematic error that could inflate the signal count artificially. They found none. The result was published in September of 2024. The golden channel decay of the charged kaon was happening at a rate roughly 50% higher than the standard model predicted. 1 in 10 billion events should produce this decay, according to the theory. The experiment found it happening 1.5 times as often as that. 50%. That is enormous by particle physics standards. Most anomalies show deviations of 10 or 15%. A 50% excess in a decay channel, this rare means something is dramatically wrong with the prediction, with reality, or with both. The statistical significance of the result hit 5 sigma, the threshold for a discovery in particle physics. 5 sigma means the probability that the result is a random statistical accident is roughly 1 in 3.5 million. To put that in terms, you can imagine rolling a die and needing to roll a 6. Then imagine doing that successfully 22 times in a row. The odds of the kaon anomaly being chance fluctuation are smaller than that. 5 sigma is the level at which physicists stop saying anomaly and start saying discovery. The Higgs boson was announced at 5 sigma in 2012. The charged kaon golden channel excess reached the same threshold in 2024. Physicists were not celebrating. They were worried. The reason is the nature of the decay itself. The golden channel is special because it is theoretically clean. Unlike messier decay channels, where many particles interact and corrections stack up. The golden channel involves a small number of particles in a well-constrained process. The Standard Model's prediction for this decay is one of the most precise and reliable calculations in all of particle physics. There is very little room for the prediction to be wrong due to theoretical uncertainty alone. That precision is what makes the 50% excess so alarming. If the prediction is accurate, then the only way to explain a 50% excess is by adding something new to the process, a new particle or force contributing to the decay rate, boosting it above the Standard Model expectation, something that couples to the strange quark and to the neutrino pair, something that slips into the quantum process and adds a new pathway that the theory never counted. The structure of the decay puts sharp constraints on what that something could be. It must interact with quarks. It must produce invisible final state particles consistent with neutrinos. It must carry the right quantum numbers to participate in the decay without being vetoed by the experiment's background rejection. Very few theoretical candidates survive those constraints. Some do, and the theorists who studied those candidates noticed something that sent a chill through the field. The particles that could explain the kaon anomaly were the same class of particles that could explain the B-meson anomaly. Two different experiments, two different particles, two different decay channels, the same theoretical suspects. When a charged kaon decays through the golden channel, three particles emerge: a charged pion, a neutrino, and an antimatter neutrino. That combination is the entire output of one of the rarest processes in particle physics. The pion is the easy one. It carries electric charge, which means it interacts with the detector's electromagnetic fields and leaves a track. Sensors record its path as it curves through the magnetic regions of the experiment. From that curve, physicists extract the pion's momentum and energy with high precision. The pion is the only directly visible output of the entire decay. The neutrino and antimatter neutrino are invisible. They pass through the detector, through the walls of the tunnel, through the Earth itself without interacting with anything. Neutrinos are famous for this. Billions of them pass through your body every second, originating from the sun, and you feel nothing. The Na-62 experiment cannot see them at all, so how do scientists know they were produced? The answer is conservation. Physics laws require that energy and momentum are conserved in every interaction. Whatever the kaon carried in, the decay products must carry out. The pion's measured momentum accounts for only part of the kaon's total momentum. The remainder went somewhere. That somewhere is the two invisible neutrinos. Their presence is inferred from the missing energy in the system. This makes the golden channel decay one of the most subtle measurements in particle physics. Every other possible explanation for the missing energy must be ruled out before neutrinos can be claimed as the answer. Photons can carry away missing energy. Other light-neutral particles can escape detection. Every background must be systematically addressed. The experiment spent enormous effort on this problem. The downstream veto detector was specifically designed to catch any photon or neutral particle that might mimic missing energy. Anything that registers in the veto means the event is rejected. Only events where the missing energy remains genuinely undetected pass the selection. The antimatter neutrino in the golden channel decay is also invisible, but its existence matters for a different reason. The presence of an antimatter neutrino in the final state places constraints on the quantum numbers of the process. It means the decay must respect a set of conservation rules involving lepton number, the accounting system that tracks matter and antimatter in particle interactions. Any new particle contributing to this decay has to respect those same rules or produce a different final state that the veto system would catch. This is why the golden channel is theoretically clean and experimentally reliable at the same time. The invisible particles are constrained by conservation laws. Their properties are fixed by the structure of the decay. A 50% excess in the rate of this specific process means the new contribution must fit inside a very specific box defined by the rules of the decay itself. Whatever is causing the excess is not a vague, undifferentiated new physics. It is something specific, something with defined quantum properties, something that interacts with strange quarks and produces neutrino-like invisibles at a higher rate than the standard model allows. That description matches only a handful of theoretical candidates, and the theorists studying those candidates had already been thinking about the B meson. The overlap was starting to look less like coincidence and more like a pattern. Two separate signals, one hidden cause. And the implications of that cause were about to reshape how physicists thought about the universe itself. One anomaly is a warning, two anomalies pointing in the same direction is a crisis. The B meson decay broke lepton universality. The kaon golden channel exceeded its predicted rate by 50%. These two results came from different experiments, different particles, different decay processes, and different detector technologies. The teams working on each one operated independently. Their analysis pipelines were built separately. Their systematic uncertainties came from different sources, and yet both results pointed toward the same gap in the standard model. Both suggested that something outside the known framework was participating in weak force decays involving quarks and leptons. Both were inconsistent with a universe where the standard model is complete. In science, independent confirmation is the gold standard. A single experiment can be wrong in ways that even careful analysis misses. Detector quirks, software bugs, subtle calibration drifts, sampling biases, these are all real and all have fooled physicists before. The history of particle physics includes several results that reached 3 or 4 sigma significance, and then disappeared when more data arrived or a systematic error was discovered. But when two independent experiments using different particles and different detectors both produce anomalies that the same theoretical framework can explain, the probability that both are wrong in the same direction due to chance becomes vanishingly small. The B meson anomaly sat at 4 sigma. The kaon anomaly sat at 5. Together, their combined statistical weight exceeded any individual threshold. Physicists doing joint analyses of both datasets found that the combined significance approached a level that almost no known systematic error could produce. The theoretical implications were stark. The standard model's weak force sector, the part of the framework responsible for radioactive decay, quark transformations, and neutrino interactions, appeared to contain a gap. Something was interacting in that sector that the standard model had never predicted. Whatever it was, it affected muon production in B meson decays and boosted the rate of kaon golden channel decays. Both effects pointed to a new particle or force that coupled to quarks and to certain lepton types with unexpected strength. The overlap between the two anomalies constrained the theoretical possibilities considerably. A new particle that could explain one anomaly but not the other was less interesting than one that could explain both. Physicists began checking their candidate particles against both datasets simultaneously, looking for a single model that fit all the data at once. Some candidates were eliminated immediately, others survived. The surviving candidates shared certain properties. They coupled to quarks, they interacted with leptons in a non-universal way, and they carried quantum numbers consistent with the conservation laws governing both decays. That short list of surviving candidates had names that physicists had been writing about in theoretical papers for years without expecting them to become urgent. Those names were about to become very important. The first one was the leptoquark, a particle so deeply strange that it blurs the boundary between two categories of matter that physicists had always kept separate. The standard model divides all matter particles into 2 separate families: quarks, which make up protons and neutrons and exist only inside larger particles, and leptons, which include electrons and neutrinos and move freely through the universe. These 2 families are distinct. They obey different rules. They interact with different forces. In 60 years of particle physics, no confirmed experiment has ever seen a particle that belongs to both categories at once. A leptoquark would change that. A leptoquark is a theoretical particle that carries the quantum numbers of both a quark and a lepton simultaneously. It couples to quarks and leptons at the same time, meaning it can appear as an intermediary in a process that transforms one type of particle into the other. It would be a bridge between the two matter families that the Standard Model insists should never communicate directly. The idea is old. Leptoquarks were proposed in the 1970s as part of attempts to build a more unified theory of particle physics. Grand unified theories, which try to merge all three non-gravitational forces into a single framework, often predict leptoquarks as natural consequences of the unification. They have been searched for in accelerators for decades. No one has found one, but no one has found evidence that they definitely do not exist either. The searchers simply set lower limits on how heavy a leptoquark would have to be to have escaped detection so far. In the context of the B meson anomaly, a leptoquark works like this. As the B meson decays through the electroweak penguin process, a leptoquark could slip into the quantum loop alongside the Standard Model particles. It would couple to the beauty quark on one side of the loop and to the muon on the other. Its presence would alter the ratio of muon production to electron production because the leptoquark's coupling strength to muons differs from its coupling to electrons. In plain terms, the leptoquark would act as a new pathway through the decay loop that preferentially affects muon production. It would not replace the Standard Model process. It would add to it, skewing the output in a way that breaks the equal treatment assumption of lepton universality. For the kaon anomaly, the same particle could contribute differently. A leptoquark with the right properties could enhance the golden channel decay rate by providing an additional pathway for the strange quark to transform into a pion and two neutrino-like invisible particles. The 50% excess would be a direct consequence of that additional pathway operating at a rate larger than the Standard Model's single pathway. The appeal of the leptoquark as an explanation is that a single particle with a single set of defined properties could account for both anomalies simultaneously. That parsimony, one new thing explaining two separate mysteries, is exactly the kind of pattern that physics has repeatedly found to point towards something real. The problem is that nobody has seen a leptoquark. Every search has found nothing. The particle, if it exists, must be heavier than any accelerator has yet been able to produce directly. It would be operating as a virtual particle, borrowing energy from the quantum vacuum to appear briefly inside decay loops without ever materializing as a real, detectable object. That invisibility is frustrating, and it is also exactly what a second theoretical candidate relies on to explain the same data. Every force has a messenger. Electromagnetism uses photons. The strong force uses gluons. The weak force uses particles called W and Z bosons. These force-carrying particles are the mechanism by which forces act. When two electrons repel each other, they exchange photons. The photons carry the force between them. The Standard Model accounts for 3 of the 4 fundamental forces this way. Each force has its carrier. The carriers are described by the model's equations. Their masses, their interaction strengths, and their quantum numbers are all precisely calculated and precisely confirmed by experiments. But the Standard Model does not forbid the existence of additional force carriers. It simply does not predict any. If a new force exists, it would need a carrier. Physicists call the most common theoretical version of a new force carrier the Z-prime boson. The name references the Z boson of the Standard Model, the neutral carrier of the weak force, and adds prime to indicate a new, heavier version with different properties. A Z-prime boson would be a completely new fundamental force operating alongside the known 4. It would interact with quarks and leptons, but with different coupling strengths for different particle types. Unlike the Standard Model's Z boson, which treats muons and electrons equally, a Z-prime could couple more strongly to muons than to electrons, or vice versa. That difference in coupling is exactly what the B meson anomaly requires. Inside the electroweak penguin decay loop, a Z-prime would appear as a virtual particle, It would carry the interaction between the beauty quark and the outgoing lepton pair, preferentially channeling the decay toward electron production and away from muon production, or the reverse, depending on the specific model. The result would be a measured lepton ratio that deviates from the standard model prediction. For the kaon decay, a Z prime with the right properties could provide an additional contribution to the golden channel rate. The kaon's strange quark could interact with the Z prime, which would then decay into a neutrino-antineutrino pair, exactly the invisible particles that the golden channel requires. More pathways through the decay process mean more events, explaining the 50% excess. The Z prime hypothesis has the same appeal as the leptoquark: one new particle, two anomalies explained. But it also raises immediate questions. A new fundamental force would have effects beyond the decays at CERN. It would have to interact with all matter to some degree. It would contribute to processes that have already been measured with great precision at other experiments. A Z prime cannot be too strongly coupled without already having shown up in existing data. This constraint is useful. It narrows the possible mass and coupling strength of the Z prime to a specific range. If the particle exists, it must be heavy enough to have escaped direct production at current accelerators, but with the right couplings to match both anomalies. Mapping those constraints tells physicists exactly where to look next. The next generation of experiments at CERN, running at higher energies with larger datasets, could either produce the Z prime directly or tighten the constraints to the point where specific theoretical models are ruled out. The answer is almost within reach, but there is another possibility waiting in the shadows that is harder to constrain and harder to test. One that would not involve a new particle in the ordinary sense at all. Most of the universe is invisible. That sentence has been known for decades and has not stopped being disturbing. Astronomers measuring the rotational speed of galaxies found in the 1970s and 80s that galaxies spin far too fast for the amount of visible matter they contain. If only the stars and gas and dust were providing gravity, the outer edges of galaxies would fly apart. They do not fly apart. Something is holding them together. Something massive. Something that produces no light, reflects no light, and interacts with light so weakly that it has never been directly detected. Physicists call it dark matter, and it makes up roughly 5 times more mass than all the ordinary matter in the universe combined. Dark matter has been confirmed indirectly through dozens of different types of observations. The way light bends around galaxy clusters, the way the cosmic microwave background fluctuates across the sky, the way large-scale structure in the universe formed over billions of years. All of these observations require dark matter to be real. The evidence is overwhelming, and yet nobody knows what dark matter is made of. Every search for dark matter particles has come up empty. Detectors buried deep underground to shield them from cosmic rays have spent years waiting for a dark matter particle to scatter off an atomic nucleus. Nothing. Satellites have searched for gamma rays that dark matter annihilation should produce. Nothing definitive. So dark matter exists, has enormous mass, and has never been directly detected. Now add the B meson and kaon anomalies. Some physicists have proposed that the force connecting dark matter to regular matter could explain both anomalies. If dark matter communicates with ordinary particles through a new mediating particle, a dark photon or a dark Z boson, that mediator might couple differently to muons than to electrons. Its virtual exchange inside decay loops could produce the lepton universality violation seen in B meson data and boost the kaon golden channel rate by providing additional decay pathways. This idea is genuinely interesting because it would connect 2 unsolved problems at once. The nature of dark matter and the CERN anomalies would both trace back to the same hidden sector of physics. A new layer of the universe operating alongside the visible one, interacting with ordinary matter through weak, previously undetected exchanges. The challenge is testability. Dark matter, by definition, interacts weakly with ordinary matter. A particle that couples strongly enough to show up in B meson decays would likely have to be lighter and more weakly coupled than most traditional dark matter candidates. Some models allow this. They predict a new dark sector with light mediators that could produce exactly the signatures seen at CERN. These models also make other predictions: small distortions in the properties of known particles, subtle effects in precision measurements of the muon's magnetic moment, a quantity already under intense scrutiny at separate experiments. If the dark sector explanation is correct, these precision measurements should show correlated deviations. Some of them already do. The muon anomalous magnetic moment, measured at an experiment in Illinois, has shown a persistent deviation from its standard model prediction for years. The same class of new particles that could explain the CERN anomalies also naturally explains the muon magnetic moment discrepancy. 3 separate observations, 1 potential common cause. The pattern was becoming hard to ignore, but the strangest explanation was still waiting. One that does not involve new particles at all. One that involves extra dimensions of space. Dimensions of space are something most people do not spend much time thinking about. Left and right, forward and back, up and down, 3 dimensions. That is the world. It is so obvious that questioning it feels absurd. Physicists do not share that comfort. Since the early 20th century, theorists have proposed that space might contain dimensions beyond the 3 we experience. These extra dimensions would be invisible to us not because they do not exist, but because they are curled up so tightly that nothing large enough to sense them ever passes through. Imagine a garden hose. Seen from a distance, it looks like a one-dimensional line. But if you zoom in, the hose has circumference, a circular cross-section that adds a second dimension. Extraspatial dimensions work similarly, existing at scales far smaller than anything human instruments can directly measure. In the 1990s, theorists proposed models where extra dimensions might be large enough to affect gravity at short distances. The idea was that gravity, uniquely weak among the 4 forces, appears weak precisely because it leaks into extra dimensions. The other 3 forces, electromagnetism, the weak force, and the strong force, are confined to our 3-dimensional world. Gravity spreads through additional dimensions and dilutes. More recent models extend this framework to explain anomalies in particle decays. In these models, the extra dimensions contain particles called Kaluza-Klein towers, which are essentially echoes of standard model particles that gain additional mass from their motion in the extra-dimensional directions. These Kaluza-Klein particles are invisible at low energies, but at the energies reached by the Large Hadron Collider, they could contribute to virtual particle loops inside decay processes. A Kaluza-Klein excitation of the Z boson, for example, would appear inside the electroweak penguin loop of the B meson decay. Its properties would differ subtly from the standard model's Z boson. It could couple differently to muons and electrons. It could alter the lepton ratio in a way that matches the observed anomaly. For the kaon-Golden channel, similar Kaluza-Klein contributions could boost the decay rate above the standard model prediction by providing additional virtual pathways. The extra-dimensional origin of these particles would explain why they have not been seen directly. They require energies beyond what current accelerators produce to materialize as real, detectable particles. What makes the extra dimensions explanation compelling is its breadth. It naturally addresses the hierarchy problem in physics, the deep puzzle of why gravity is so much weaker than the other forces. It connects the CERN anomalies to a framework that has independent theoretical motivation, and it makes predictions beyond just the decay anomalies, predictions about gravitational behavior at small scales, and about missing energy signatures at high-energy colliders. What makes it uncomfortable is that it is very difficult to test directly. Extra dimensions curl up at scales smaller than any current instrument can probe. Their effects show up only through virtual contributions to quantum processes, exactly the indirect signatures seen in the B meson and kaon data. The anomalies at CERN might be a window, a narrow one, but a window into a layer of reality that human instruments have never directly reached. And right now, the machines that could push that window open wider are generating data every second, data that algorithms are sorting and erasing and saving according to rules designed long before anyone knew these anomalies existed. Every second, the Large Hadron Collider generates an amount of raw data that would fill millions of books. The sensors surrounding the collision points record everything, every particle track, every energy deposit, every timing signal from every detector layer. The full data stream from all 4 main experiments combined would require impossible quantities of storage space and processing power to save completely. So, algorithms decide what to keep. The decision system is called a trigger. It operates in multiple stages, each one faster than the last, each one filtering the data stream more aggressively. The first stage makes a decision in less than a millionth of a second, running directly on hardware built into the detector electronics. It looks for basic signatures, high-energy tracks, unusual energy patterns, the presence of certain particle types. Events that match one or more criteria get flagged. Everything else is erased immediately. The second stage runs slightly slower and has access to more complete event data. It applies more detailed selection criteria, checking whether the flagged events actually match the patterns scientists are looking for. Some events that pass the first stage get rejected here. Others are confirmed and passed on for permanent storage. The final output, the events actually saved to disk, represent a tiny fraction of all collisions that occurred, a fraction of a percent. The rest are gone forever, overwritten by the next wave of collisions before any human could review them. This design is necessary. Storage and computing costs are finite. Experiments must prioritize. Scientists decide before a run begins which signatures they care about, program the trigger to find those signatures, and accept that everything else is discarded. But this creates a problem that the CERN anomalies have made urgent. The trigger systems were programmed based on the standard model. They were designed to find events that the known physics said would be interesting. Events that look like new particles the theory predicted. Events that probe processes the framework identified as important. Events that look like an entirely new type of physics. Something the standard model never described might not match any trigger criteria. They might look too ordinary from the trigger's perspective. They might share signatures with background events that the trigger is programmed to discard. They could have been happening in every run for years, passing through the detector and vanishing before any algorithm had the chance to save them. Scientists call this the trigger bias problem. The machine is collecting data, but the data it keeps was selected by rules designed around old assumptions. If the new physics produces unexpected signatures, those signatures might be systematically filtered out before anyone can study them. The CERN collaborations have been aware of this problem for years and have taken steps to address it. One approach is called data scouting or data parking, where a stripped-down version of each event, containing only basic information, is saved for every collision rather than the full detailed record. This allows a second look at events the trigger would normally discard, using the stripped data to identify anything unexpected that slipped through the cracks. Another approach is machine learning. Instead of programming specific signatures into the trigger, scientists train algorithms on simulated data and let them learn which events look unusual in any way. Anomaly detection systems flag events that deviate from typical patterns without requiring the physicists to specify in advance what the deviation looks like. These new tools are helping, but they are a reminder that what CERN has found so far might be a fraction of what is actually happening inside those collisions. The machine knows more than scientists have been allowed to see. There is a layer of strangeness to CERN that has nothing to do with anomalies or undiscovered particles. It lives in the engineering itself, in the sheer physical reality of what it takes to run the largest machine ever built. The pipes inside the Large Hadron Collider are kept at a temperature of -456 degrees Fahrenheit. To put that in context, the average temperature of outer space, far from any star, is roughly -455 degrees Fahrenheit. The bamepipe of the Large Hadron Collider is colder than the void between galaxies. This extreme cold is not for the particles, it is for the magnets. The superconducting electromagnets that bend and focus the particle beam need to operate in a state called superconductivity. In this state, electrical current flows through the magnets without any resistance. Without superconductivity, the magnets would generate enormous heat from electrical resistance and immediately burn out. With it, they maintain their powerful, precisely shaped fields indefinitely. Superconductivity requires cold. The specific alloy used in the Large Hadron Collider's magnets, a combination of niobium and titanium, becomes superconducting only below roughly -452 degrees Fahrenheit. The system chills the entire 27-kilometer ring to below that threshold, using a massive refrigeration infrastructure. The machine is one of the largest cryogenic systems on Earth. The vacuum inside the beam pipe adds another layer of engineering. Particles traveling at nearly the speed of light will scatter if they collide with air molecules. Even a trace amount of gas inside the pipe would knock the beam apart before it could complete a single lap. So the vacuum is maintained at a pressure 10 trillion times lower than sea-level atmospheric pressure. The inside of the beam pipe is emptier than the space between stars in our galaxy. The beam itself carries energy comparable to a high-speed train collision. Two beams, each one traveling in opposite directions around the ring, contain the combined energy of two fully loaded aircraft carriers moving at highway speed. When those beams cross and collide at the 4 detector locations, that energy compresses into a space far smaller than a proton. Every system in the machine operates under conditions that would destroy conventional electronics or materials. The radiation environment near the collision points is intense enough to damage sensors over time. Scientists replace detector components regularly as radiation accumulates. The magnets are tested to verify their superconducting properties and recertified before every major run. All of this is happening beneath towns, farms, and roads on the French-Swiss border. Residents above ground feel nothing. The machine does not vibrate. It does not make noise at the surface. The only sign that something extraordinary is happening hundreds of feet below is the occasional access shaft entrance, secured behind a fence, looking like any other industrial facility. Inside, the coldest, emptiest environment humans have ever created produces the hottest, densest conditions that have existed on Earth since moments after the Big Bang. And all of that effort exists for one purpose: to see what the universe is made of at the deepest level, to answer questions the standard model raised and could not answer itself. The machine is extraordinary, and increasingly, the evidence suggests its findings are revolutionary. Numbers describe the Large Hadron Collider well: 16 miles around, 328 feet underground, temperatures colder than space, vacuums emptier than interstellar voids. But numbers do not capture what it actually means to stand next to it. The main detectors are the place where that scale becomes physical. The largest one, called the Atlas detector, is 46 meters long and 25 meters tall. That is roughly the size of an 8-story building lying on its side. It weighs about 7,000 tons. Heavier than the Eiffel Tower. It sits in an underground cavern the size of a cathedral, surrounded by layers of sensor technology that extend from the collision point outward like a series of concentric shells. Building the detector required assembling components built by engineers and scientists in hundreds of institutions across dozens of countries and shipping them underground through access shafts. Some pieces were too large to move once they arrived in the cavern. They had to be assembled in place, with workers descending into the underground hall and building the detector layer by layer around the central beam axis. The tunnel itself runs through a mix of rock types. Much of it passes through a soft, stable limestone called molasse, which was chosen deliberately because it is easy to cut and does not let water in easily. The tunnel was bored using massive machines that cut through rock and installed concrete segments in a continuous process. Workers spent years underground completing the ring. The 16-mile circumference passes beneath the territory of both France and Switzerland. No border crossing is needed to travel around the ring because the tunnel predates any modern security concern about such things. But the international scope of the project is reflected in the collaboration itself. Physicists from over 100 countries contribute to the experiments running at CERN. The collaboration that runs the Large Hadron Collider Beauty experiment alone includes hundreds of researchers from institutions across Europe, the Americas, and Asia. The control rooms where operators monitor the machine are filled with screens showing the current status of thousands of individual systems. Magnet temperatures, beam intensity, vacuum pressure, detector response. An alarm anywhere in the 16-mile ring shows up immediately on the central displays. Problems that used to require hours to diagnose in older machines can now be traced in minutes through the monitoring infrastructure. The people running the machine work in shifts around the clock, operators managing the beam, engineers responding to faults, physicists monitoring the quality of the data coming from the detectors. During high-intensity run periods, the machine operates continuously for months, accumulating collisions at a rate too fast for human monitoring to track individually. What happens in that tunnel is among the most collaborative scientific endeavors in human history. The machine is a tool. The anomalies it found are real. But behind every result is a structure of human effort so large and so carefully organized that it constitutes its own kind of wonder. And the results that structure has produced are now forcing a conversation about whether the universe operates on rules humanity has not yet written down. Strip away the technical language and the statistical thresholds and the particle names, and the B-meson anomaly is saying something simple. The forces of nature have a preference. They treat muons differently from electrons. They tip the scale. They play favorites. That does not sound catastrophic. It sounds like a detail, a small imbalance in some obscure particle decay. But the implications reach far deeper than the particle itself. Lepton universality is baked into the foundation of the Standard Model. It is not an assumption that sits off to the side where it can be quietly revised without disturbing anything else. It is embedded in the equations, the mathematics of the weak force, the calculations of decay rates, the predictions for every interaction involving leptons. All of them assume that muons and electrons and tau particles are treated identically by the fundamental forces, up to the difference in their masses. If that assumption fails, the equations fail with it. Every calculation in the Standard Model that involves lepton universality carries an error. Every prediction built on those calculations needs to be re-examined. The framework does not collapse instantly, but it develops a fault line that runs through its entire structure. More concretely, breaking lepton universality would mean that two particles, which appear identical except for mass, are experiencing the universe differently at the level of fundamental forces. An electron and a muon interacting with the weak force would be governed by subtly different rules. The symmetry that physicists considered absolute would turn out to be approximate, holding at low energies but breaking down under certain conditions. That kind of approximate symmetry is a known phenomenon in physics. The Standard Model itself contains approximate symmetries that break under specific circumstances. Symmetry breaking is, in fact, the mechanism behind mass itself. The Higgs field breaks a symmetry that would otherwise make all particles massless. So lepton universality breaking is physically conceivable. The question is, what breaks it? A broken symmetry requires a mechanism. Something physical must be responsible for the breaking. An unknown particle, a new force, a hidden field operating at a scale above what current accelerators reach. Identifying that mechanism would not just explain the B-meson anomaly, it would add a new layer to the map of fundamental physics. Every time physics has encountered a broken symmetry, something new was waiting on the other side. The breaking of the electroweak symmetry led to the Higgs boson. The violation of charge parity symmetry in kaon decays pointed toward the mechanism that allowed matter to survive after the Big Bang. Broken symmetries are not failures of the theory. They are signposts toward deeper structure. Lepton universality breaking would be the most significant signpost in decades. It would tell physicists that a new layer of physics is operating at a scale just above current experimental reach, a layer that interacts with muons and quarks in ways the standard model never described. The machine at CERN is pointing at that layer. The anomalies are the fingerprints of whatever lives there. Identifying what leaves those fingerprints is the most urgent problem in experimental physics right now. And history suggests that every time physics found something this persistent and this precise, a genuine discovery was close behind. The history of physics is a history of confident frameworks being shattered and rebuilt stronger. Every generation of scientists has inherited a set of rules they trusted completely, and every generation has watched those rules fail at the edges of new experiments, revealing something larger beneath them. Isaac Newton built a framework for motion and gravity that worked perfectly for 200 years. Planets, cannonballs, and falling apples all obeyed his equations without exception. Engineers built bridges and ships, and eventually steam engines using his predictions. The framework felt complete. Then James Clerk Maxwell unified electricity and magnetism and showed that light was an electromagnetic wave. The equations implied that light had a fixed speed, regardless of how fast the observer was moving. Newton's framework, which assumed time and space were absolute and unchanging, could not accommodate this. Something had to give. Albert Einstein broke Newton. Special relativity replaced absolute time with relative time. Space and time merged into a single four-dimensional fabric. Newton's equations survived as a useful approximation at low speeds. But the deeper truth was stranger and more profound than anyone had imagined. Then, quantum mechanics shattered the picture again. At the smallest scales, particles did not follow definite paths. They existed in superpositions of multiple states simultaneously. Measurements influenced outcomes. Certainty was replaced by probability. Einstein spent the last decades of his life uncomfortable with quantum mechanics. The universe, it turned out, did not care about his discomfort. The Standard Model was the next great synthesis. It absorbed quantum mechanics and special relativity and added descriptions of the strong and weak nuclear forces. It predicted the Higgs boson 50 years before the Large Hadron Collider found it. It is the most tested scientific theory in history, and it is failing its latest tests. The pattern is clear. Every time a framework breaks, the replacement does not erase what came before. Newton's equations still work for everyday engineering. Quantum mechanics does not contradict relativity. It requires it. Each new framework contains the old one as a special case, valid within limits, and extends beyond those limits into new territory. The framework that replaces or extends the Standard Model will do the same. It will reproduce every correct prediction the Standard Model makes and add new predictions for the phenomena that the Standard Model cannot reach. Dark matter, quantum gravity, the origin of the matter-antimatter imbalance, and now the lepton universality breaking seen in B-meson and kaon decays will all have to fit inside the new framework. Physicists do not yet know what that framework looks like, but they know the shape of the gap. The anomalies at CERN define its boundaries. Whatever new physics is operating, there must couple quarks to leptons with unequal force, must produce the specific decay signatures observed, and must remain consistent with every other precision measurement that has returned Standard Model predictions. Those constraints are a gift. They are the outline of the next framework, waiting to be filled in. Scientists have been here before. The view from inside a paradigm shift always feels uncertain. The evidence points somewhere, but the destination is not yet visible. Every time before, the destination turned out to be worth the journey. The most elegant possibility is one new particle or one new force explaining everything. The B-meson anomaly and the kaon anomaly and the muon magnetic moment discrepancy, and possibly the ghost in the accelerator, all tracing back to a single hidden source. One gap in the Standard Model, one piece of physics sitting just beyond current experimental reach, pulling strings in multiple places simultaneously. Physicists love elegance. History has repeatedly rewarded it. Maxwell unified electricity and magnetism into one framework. The electroweak theory unified electromagnetism and the weak force. The appeal of unification is deep in the culture of the field. But the universe does not always cooperate. The anomalies at CERN might have separate causes. The Bemerson-lepton universality violation might trace to a leptoquark. The kaon golden channel excess might come from a different new particle entirely, a heavy neutral boson with different coupling properties. The muon magnetic moment discrepancy might originate in a dark sector mediator unrelated to either. 3 separate gaps in the standard model, each one real, each one pointing a different direction. This possibility is harder to work with, but equally valid. The standard model is already known to be incomplete. There is no theoretical reason why there should be exactly one missing piece. The history of particle discoveries suggests the opposite. Every time a new layer of physics was found, it contained multiple new particles, not just one. The quarks, when discovered, came in 6 types. The leptons come in 3 generations. The force carriers form a family. Whatever lies beyond the standard model likely has its own family structure, its own generations, its own set of relationships. One new particle might be the first of many. Physicists are using the constraints from both anomalies to map the possibilities. A particle that can explain both the B-meson and kaon results with a single set of parameters would have a highly specific mass and coupling pattern. If that pattern matches additional observations, such as precision measurements of the muon magnetic moment or subtle deviations in other rare decay channels, the case for a single common cause becomes much stronger. If the anomalies require different explanations with different parameters, the picture becomes more complicated but also richer. Multiple new particles would mean a new sector of physics, a new family of interactions operating at a scale above the standard model's reach. Either way, the anomalies at CERN have defined a target. The next generation of experiments at CERN, running at higher collision energies with more sensitive detectors, will either find the particle directly or accumulate enough data to determine precisely what combination of new physics can reproduce all the observed signals. The answer is within reach. Not today. The anomalies are real, the theoretical candidates are defined, and the experimental roadmap is written. What happens next depends entirely on what the universe is willing to reveal when pushed harder than it has ever been pushed before. And the pushing is already underway. Physics has had theories before that felt permanent and then were not. The standard model is not the end of science. It is a chapter, and the anomalies at CERN are turning the page. The theories waiting to replace or extend the standard model have been developed by theorists for decades. Some were written as elegant mathematical constructs with no experimental motivation. Others emerged from specific attempts to solve the gaps the standard model left open. Now, with experimental data pointing at new physics for the first time in years, those theories are being tested against reality. Supersymmetry is the oldest and most studied candidate. It proposes that every known particle has a partner particle with different spin properties. The partners of quarks are called squarks. The partners of leptons are called sleptons. The partners of force carriers are called gaugenos. Supersymmetry naturally explains why the Higgs boson mass does not spiral to enormous values through quantum corrections, a problem called the hierarchy problem that the standard model cannot solve internally. Supersymmetric partners also provide dark matter candidates. The lightest supersymmetric particle, stable and electrically neutral, would behave exactly as dark matter observations require. It would fill the missing mass in galaxies without interacting with light. The Large Hadron Collider has been searching for supersymmetric particles since it turned on. It has not found them. This has ruled out large regions of the supersymmetric landscape and forced theorists to adjust their models, pushing the partner particles to higher masses or more complicated configurations. But the theory survives. It makes predictions that future, higher energy experiments can test. Extra dimensions models, offer another path forward. Several theoretical frameworks predict that gravity spreads through additional spatial dimensions, explaining its weakness relative to the other forces. These models make predictions for high-energy colliders, missing energy from gravitons leaking into extra dimensions, new Kaluza-Klein excitations of standard model particles appearing as heavy resonances in collision data. Future collider experiments could find these signatures directly. Compositeness is a third direction. The standard model treats quarks and leptons as fundamental, with no internal structure. Compositeness models propose that they are made of even smaller constituents, just as protons are made of quarks. At high enough energies, the internal structure would reveal itself through deviations in particle interactions. The scale at which this would appear is not yet constrained by data. All of these frameworks make predictions for the anomalies seen in B-meson and kaon decays. All of them can accommodate new particles that couple quarks and leptons with non-universal force. The question is which of them, if any, correctly describes what is actually happening. The next phase of CERN's operation, with upgraded detectors and higher luminosity, will generate datasets 10 times larger than what produced the current anomalies. If the anomalies are real, they will grow in significance. The theoretical candidates will be tested against increasingly precise data, and the machine is already running. The Large Hadron Collider does not stop. Between scheduled maintenance periods, it runs around the clock. Collisions happen every 25 nanoseconds. Data flows continuously from 4 main detector systems. Algorithms sort, filter, and save. Servers store. Physicists analyze. Right now, at this moment, the machine is generating collisions. Some of those collisions are producing B-mesons. Some of those B-mesons are decaying through the electroweak penguin channel. Some of those decays are producing the anomalous lepton ratios that have already reached 4 sigma significance. Each new collision adds to the dataset. The significance grows. At CERN's fixed target facilities, beams of protons are hitting stationary targets. Kaons are forming. Some of them are decaying through the golden channel. Each one counted adds to the evidence that already cleared 5 sigma. The data being collected today will not be fully analyzed for months or years. Particle physics analysis is slow. Events must be reconstructed from raw detector signals. Calibrations must be applied. Backgrounds must be modeled and subtracted. Statistical analyses must be designed, cross-checked, and independently verified. The process is careful by design because the stakes of a false discovery are high and the history of prematurely announced results is painful. But the accumulation is real. The anomalies that exist in the current dataset will either grow or shrink as more data arrives. If they grow, as the trend suggests, the statistical significance will eventually cross into territory that forces a definitive answer. The standard model cannot be patched at 5 sigma or 6 sigma. At some threshold, the evidence requires a new framework. The timing of that threshold is unknown. It could be months away. It could be years. The Large Hadron Collider's next major upgrade is designed to increase collision rates by a factor of 10, dramatically accelerating the pace of discovery. The high-luminosity Large Hadron Collider, scheduled to begin operations later in this decade, would produce enough data in its first few years to either confirm the anomalies as genuine new physics or rule out entire classes of theoretical candidates. The ghost in the machine was real. The B-meson deviation is real at 4 sigma. The kaon excess is real at 5 sigma. The muon magnetic moment discrepancy has been building for years at separate facilities. The pattern is there. The direction is clear. Something is operating in the universe that the standard model does not describe. Something that touches muons and quarks in ways the rulebook never captured. Something that has been leaving fingerprints in particle decays for years, building up slowly in datasets that are now large enough to make those fingerprints impossible to dismiss. The most powerful scientific instrument humans have ever built is underground right now, running cold and fast and empty, smashing protons together billions of times a second and recording the results. The answer is almost certainly already in the data, waiting, hidden in a fraction of 650 billion collisions, or in the 10 billion more that arrive this week, or the 10 billion after that. Physics found the Higgs. It found gravitational waves. It found quarks and gluons and neutrino oscillations. Every time the universe had something new to say, patient and precise experiments eventually heard it. The universe is talking again. The only question left is whether we are ready to listen.